So yesterday, I guess we had the idea of the Squeeze theorem and or the Sandwich theorem, however you say it, and we saw how can we use the laws of the limit. We saw at least one example of each and tried to see how does it work. Obviously, we'll see more examples, no doubts on that. Today, we'll see something really, really interesting, as I said. You'll see how infinite limits work, okay? Um, to give you an idea, let's start with this graph. This is the graph of 1 over x squared. So if you have a graphing tool, if you try to draw this 1 over x squared, you'll see the graph will look like this. Now, how does this take us to the idea of infinite limit? Or what are the conclusions we can draw from this? Let's see that. So first of all, let's forget about the graph. Let's try algebraically, okay? So we know if we plug in a value of x, in return we get a corresponding value for the function, right? Because x is the independent variable. So if we take any value, obviously, which is not making our function undefined, or in other words, for a fraction, it's not making our denominator 0, we can take any value from the real number line and see the corresponding value, corresponding functional value, right? So if we start taking values like this, 0.1, 0.01, 0.001, so on and so forth, you'll see the corresponding functional value will actually get increased, will get bigger, bigger, and bigger. The less you're picking up, the less value you're picking up, the bigger fraction you're taking for x, the larger the value will be. And you can cross-check it using your calculator. Okay, now what does this give us? So we can see that the more we are going towards 0, as you can see, this is getting smaller, smaller, and smaller, right? 0.01 is definitely smaller than 0.1, and 0.001 is definitely smaller than the previous two. So we are going towards 0, where we are getting or taking smaller values, which is going towards 0, and the value is getting bigger and bigger. So if we move really, really, really close to 0, you can imagine the value will be really, really, really big, right? Excuse me. So how big can it be? How far can we go? Can you imagine? Anyone?
Infinite? You're asking about the number itself, right?
Sorry?
The x value or the function
value? The functional value, yeah.
I mean, since you have basically an infinite amount of numbers you can put in there, just keep adding like zeros to it.
Right.
And the number will just keep increasing every time. So I guess you'd have an infinite number.
Exactly, because yeah, thank you. So if we increase the number of zeros in the fraction, we see the number of zeros here also gets increased. So that means if we go really, really close to 0, that means if the value is really small, teeny and tiny, then this functional value will be really, really big. So how big can we imagine? It can go up to infinity, can't we? So that means even if we don't know how the graph looks like, we can clearly see it from the algebraic calculation that if we move towards 0 from either side, by the way, you can see there is a plus or minus. That means we are moving from either side. We are taking plus 0.00001 and minus 0.00001. So that means we are moving from each side And either way, we can see the value is actually approaching for a larger one, for a really, really big value. So that means we can, even without eyeballing the graph, we can say that if we approach, if not we, I should say, if x approaches towards 0 from either side, the graph will actually approach, or the function will actually approach towards infinity. Do you agree? Don't look at the graph. Just try to use this calculation. If you have any doubts, you can try this, like try 0.20 then 1, and you will see your calculator won't be able to hold the number, hold the function, or show the functional value. So that means it's going towards that infinity from either side, because we have a squared function here. I mean, we have an even function. That means even if you take a negative value of x, this square will actually make it positive. So that's why you can see we don't have anything negative here, right? That's the algebraic part, by the way. But for the limit, do you agree that it should, from either side, if x approaches to 0, the value, the functional value, or the function, I would say, approaches to infinity? Do you agree?
Yeah.
Is there anyone who has still questions about it, or who is confused what's going on here? Does it make sense?
Yeah. Yeah, it makes sense.
Perfect. Now let's look at the graph. It will be much easier for us to visualize the things we have just said in words. We can actually now visualize by eyeballing the graph. So let's see. So let's move from the left towards 0. Okay. So we are calculating the left-sided limit. Okay. We are moving from the left towards 0. Okay. We're moving from the left towards 0. And you can see the graph is moving towards this. And how far can it go? Obviously, you can see that it's getting really close to this y-axis, but not really touching it. Even if you take a really, really small value near 0, you will see the value will not touch the y-axis. It will keep going, pretty close to the y-axis, but it will never touch it. We'll come to the concept of that as well soon. Soon after we finish this content. That's another topic. We say that it's an asymptote where the graph doesn't really cross that particular line. We'll come to that later. Okay. But again, you can see as you are moving towards 0, the graph is actually, the function is actually moving towards infinity from the left. So can I conclude the left-sided limit is infinity? Can I say that? Obviously when x approaches to 0.
Yes.
Let's try the right-sided limit now. So we are moving from the right. Now again, we're moving towards 0, and the function is moving towards positive infinity again. Again, it's as we are moving closer and closer to 0, the value is going closer and closer to y-axis, but it will not touch it. It will never touch it. It will keep moving upwards towards the mega infinity. Excuse me. So again, we can conclude that the right-sided limit excuse me, is indeed infinity. Do you agree?
Yes.
Is there anyone who still has confusions about it? No worries, I can try to convince you in other ways. Maybe other ways, I'm not sure. Okay, now a quick question, a really, really quick question. What is the limit of this function when x approaches to 0, when x tends to 0? And why?
Could you do that since you'd have a 0 in the denominator?
No, I don't have a 0 in the denominator because I'm moving towards it. I'm not really plugging it in.
Oh, okay. Yeah, I get what you're saying. The limit would be infinity, right?
And why?
Well, because the left side, the limit of the left side would be infinity. We'd be going towards infinity, and so would the right side. So
exactly, yeah, very good. Yeah. So since the left and right sided limits are the same, so we say the limit of this function when x tends to 0 is infinity. So that is the infinite limit we are talking about when we started. Okay. Any questions from this?
I just have one kind of small question, and I know you kind of mentioned it earlier with asymptotes, but could we just like consider this as an asymptote, or I guess kind of almost like a double asymptote because they're approaching 0 but never truly reach 0?
Exactly. Very good. Yeah.
Okay.
Yeah, definitely.
Okay. Thank you.
Very good. Very good assumption. Okay, let's move on then. Okay, so let's try and see the definition first, and then we'll come back to the graph. Okay, so it says if our function grows arbitrarily large, if it keeps increasing and obviously indefinitely, that means there is no stopping, no real stopping of that when x is approaching towards a particular value, say a, then we say that the limit of that function is infinity. Okay, and if it grows arbitrarily large in magnitude for all x sufficiently close to a, I mean, I should say not grows, I should rephrase it, if it decreases arbitrarily, or in other words, I can say if the function is negative and it keeps growing, whichever you like. If the function is negative and it keeps growing, it's the other way of saying the function is decreasing, right? So then we say the function, or rather the limit of the function is negative infinity, okay? And if you remember, I did say it last time for a really, really brief discussion about it, that when you have infinity, or rather when you have, I guess I said, yeah, when you have something over 0, then we say that limit does not exist. Do you remember? I did say that, if I remember correctly. So when you have anything over 0, that means when the denominator is 0, we did say the limit does not exist. Or to express it mathematically, we often use infinity in place of that. Not always, you will see some examples of it as well, no worries. So you can actually replace anything over infinity or anything over 0 by an infinity. You can rewrite anything over 0, replacing by an infinity. So if we see an infinity as the limit, what should we say? Shouldn't we say the limit does not exist? Do you agree?
Yeah, since it's not a set number.
Exactly. And you can actually, try to imagine in English as well. when we say limit, that means we're trying to restrict it, right? We're trying to see which value it does not exist in either way, you know, uh, from from the upper side or the left or the lower side, or from the right or left. From either side, it should not exceed that value, or we say we restrict it. In English, by limit we say we restrict something, right? But this can't be restricted to anything, right? It's actually going towards the mega infinity. How can we restrict it? So we say the limit does not exist. Any question from this definition? I know it kind of looks obvious, but still.
I have a question. I have a question.
Yeah, sure.
All right. So since we don't consider infinity an actual number, what would we call it then? Is it it's not a value, or is it a concept?
It's not a value. Yeah, you're right. So infinity is itself something we actually call it infinity. We don't try to keep it, or rather, we don't try to make it fall into any of the categories. It doesn't really fall into any set of numbers. But yeah, it does exist because there has to be something really, really big. We need to define something, right? So that's why we have defined infinity mathematically, which we, in other words, I might say, whatever we can't really see, or can't really visualize, or can't really write numerically, or we can't really do anything with that. We can't really play with that. We can't add this. We can't divide it. That's what we say that it should be infinity. That means it's actually beyond our expectation, or beyond our capacity, you might say.
Interesting. Thank you.
Another question I have.
Mhm.
So although we define the limit as infinity, it's just kind of like a reiteration. So we place infinity almost kind of like a placeholder just to kind of say it. But I noticed that it said in both cases the limit does not exist, even though we put that it's infinity.
Mhm.
That's what we do in these
Yeah,
cases.
you can, whenever you are solving it, if you are doing a multiple choice question, you will definitely have one of the options. Either you will have the infinity or does not exist. You will not have both. When you are showing your work, you can try any of the formats. I absolutely don't mind.
Okay, thank you.
So for example, if you take the whole numbers, 0, 1, 2, 3, 4, or -1, 2, 3, -2, -3, -4, how far can you go? You can actually keep calculating it. Even for million of years, you can keep calculating. So we can't really stop. We can't really see the ending. That's why I say for the whole number, there is a positive infinity at the end and the negative infinity. I mean, at one end, we have positive infinity, and at the other end, we have negative infinity. That means there is no real stopping of it. You can keep doing that. So we actually try to, try to write the set which has an ending. Although infinity is not the ending, but we try to end it with an infinity. That means it actually keeps going. You might say that. Does it answer your question?
Yes.
Okay. What do we have next? I think we have. Okay. Let's see these graphs again. So when you are approaching towards a value, let's say a, again, for calculating limit, what's the first things we need to do? If you remember, anyone?
We need
On the
to
left
set,
and right hand side.
Exactly, we need to find the limits from each side. So what we do, let's say we start with the left-sided limit. We start approaching towards a, and you can see the graph is actually moving towards infinity. So we can see the graph is growing arbitrarily. It's not really stopping. It grows arbitrarily large, and to the positive side, of course. Okay, because the function is positive, because you can see the x-axis, anything over that x-axis is always positive, right? And anything below this x-axis is always negative. That's the basic idea of Cartesian coordinates. And similarly, from the right, if we are approaching towards a, you can see again the function is all part of this function is above this x-axis, so that means the function is positive, and it's moving towards this mega infinity again. It keeps growing, so that means we say that the function, the limit of the function is infinity, or you might say the limit does not exist. You can say that. There is a slight difference between writing does not exist and infinity in some cases. I'll show that when the example comes, because definitely it will come in the next couple of slides. If not today, definitely tomorrow. I'll show that to you. But anyway, we can see when the function is positive and it keeps growing arbitrarily large, we can say that it's moving towards infinity, or the limit is infinity, or in other words, the limit does not exist, even though it actually has the same two-sided, same values for the two-sided limits. Let's see what happens when the function is negative. Again, anything below this x-axis is negative, we know that. So if we are approaching towards a, and if my function keeps growing in this direction, that means we can say the function is actually decreasing, right? Because it's the negative side. So the function keeps decreasing when we are approaching towards a. Similarly for left-sided limit as well. We're approaching towards a, and the function, you can see, it actually keeps decreasing towards infinity, towards negative infinity. Or since the function is negative, we can say that it grows arbitrarily large, although it's going towards the negative infinity, since the function is negative, right? Okay, so excuse me. Let's see a more complicated one, and see. Let's see how can we interpret it, or how can we calculate the infinite limits from it. Okay, again, we'll soon see what does these dash lines mean. These lines actually mean the asymptotes, which the graph won't really cross. And we say that it's the vertical asymptote. We'll soon see the definition. But now let's see the graph of it. The function is x over x squared minus 1, the quantity squared. And we can see, if we just take the right half of the graph, we can see when we're approaching towards positive 1 from the right, the function is going to positive infinity. When we're approaching from the left towards 1, the function is again moving to positive infinity. Do you agree? by just eyeballing the graph. Do you agree with me that, yeah, we are actually, I mean, the function is actually moving towards positive infinity when we are approaching towards 1 from either side? Just consider the right half of the graph, okay? This side. Do you agree?
Yeah.
Let's see what happens for negative infinity, because you can see when you're approaching towards negative infinity from our right, the graph is now going downwards. It's getting decreased. It's going towards infinity. It's going to the mega infinity whenever we are approaching towards -1 from the right. Even from the left, we can see the graph is again decreasing and it's going towards negative infinity, right? So we say the limit when x tends to 1, the limit of this function when x tends to 1 is positive infinity from this right half. And from this left half, we can conclude that when we are approaching towards -1, the function has a limit of negative infinity. Do you agree?
Yes.
Okay.
And so for
Mhm.
for the test, I guess, or just how will we write this as an answer? Would it look just like this, where you have the limit as the function approaches
Yeah,
1 from a -1?
yeah, for the test, you will have a graph like this, maybe with more parts on your left and on your right. You'll have several more parts. Instead of only 2, you'll probably have 4. You know, 1 here as well, and another one is here. So with that graph, the question will ask you to find the limit when x tends to something extends to a certain value. Like for this one, we can eyeball that when we are approaching towards 1 or -1, it's actually approaching to infinity or negative infinity. So it will ask you like this: find the limit of this function when x tends to 1. The question will be like this. Or it will say, what will happen to the limit of this function? Or what will be the limit of this function when x approaches to -1? Okay, the question will look like this. And I'm kind of giving you the question. You'll definitely see a question like this, maybe more than one. And you don't need to calculate anything. You can just eyeball the graph and draw your conclusion. You will not need anything algebraic. You will not be required to do any algebraic calculation and using the laws and all that. Maybe the function will not be given either. I'll just give you the graph and say find the limit from this.
So just to like confirm also like about the test and stuff,
Mhm.
if you ask us to find the limit, but you just give us like the function, or like just the equation and no graph,
Mhm.
then we use that one equation that we went over on, I think it was Monday.
So for the exam on Monday, you are asking that will I just give the function and tell you to calculate the limit?
Yeah, I mean, just like we'll use, like we have an equation to find that, right?
So if you are given the expression or the function and you are asked to calculate the limit, then it will definitely not be complicated because we haven't really seen any of those. So if I ever say to calculate the limit, it will just require you to use the laws you have already seen, which are pretty obvious.
Yeah.
Okay, we will definitely see some complicated limits soon, but not for the first exam.
Okay, thank you.
Mhm. Okay. One-sided limits. Oh, I think I have something in the chat. just give me a second. Let me see that. Will the test be multiple choice or will we type in the limit? So I haven't really set up the question as yet. I'm planning to do actually a bit of both. I mean, there will be obviously multiple choice questions, and there will be at least one question where you will be asked to show your work. I'm planning to do that. Let's see. So if you are asked to show your work, then you will have options to upload your file while you are sitting for that exam, and or you could actually send it directly to me. If you are struggling to upload it to Pearson, to MyMathLab, often we have seen the case that because of the technical issues or something like that, or the student couldn't really find how to upload it, that's all right. You can send it directly to me. Okay, I'll show you. I'll show you. Yeah, I'll try to show you one screenshot how to do that, or maybe if I can't do that, maybe all of you can actually send it directly to me. You can avoid that if you want, because often we see technical issues while uploading the file. That shouldn't be a problem as long as you can take a picture of it and send it to me. Okay. All right. So, okay. So one-sided infinite limits. Excuse me. Again, it actually works the same way we have done previously. We don't need anything out of extraordinary for this. For example, when you're calculating the right-sided limit for the function, let's see this figure 2.26. Sorry. You can see if you're calculating the right-sided limit, all you need to do is to approach from the right and see where does it take us. Since we are approaching towards this a from the right, and the graph is going towards infinity, we can say that the right-sided limit is infinity. Okay, now I should say that. Now I should say, when do you need to write does not exist, and when do you need to write infinity? This is the part where you can differentiate this. In some cases it will be the same, but in these cases, if you write does not exist, that won't be the exact right answer. Can you imagine why? Anyone?
Can you repeat the question?
Yeah, so if you have a question like this, where you're calculating the right-sided limit and the limit is positive infinity, or for the same function, you're calculating the left-sided limit and the limit is negative infinity, and if your right does not exist, it will not be the right answer. It will not be the exactly precise answer. Can you imagine why?
Is it because we
Um,
know the limit does exist, we just can't actually reach it because we can get infinitely close to it?
So if the limit is infinity, we have already seen it here. The limit does not exist. I mean, whenever we get positive or negative infinity, the limit actually does not exist. But still, you should write positive infinity in this case and negative infinity in this case, because if you write does not exist here, it's not precisely saying whether it's going towards positive infinity or negative infinity. So I would rather suggest you to have it precise. That means, yeah, the limit does not exist, no doubts on that, but why, or rather which way it's going towards, we need to know that as well. Because it could be negative infinity. If you just write does not exist here, one may be confused whether it's because it's moving towards positive infinity or the negative infinity. How do I know that? So that's why if you have a question like this, I would rather suggest you to write infinity with the corresponding sign, whether it's moving towards positive infinity or negative infinity. Write that instead of does not exist. Does it make sense? Or I'll try to reiterate it maybe.
Okay, sorry, I do have a question about that actually.
Mhm.
Is this, like what you just said, is that only for if there's a one-sided infinite limit?
Yeah, mostly, because for the one-sided limit, you will definitely have a sign corresponding to it or assigned to it. If you are moving from one side, it can't be both, right? It can't be positive infinity and negative infinity at the same time. So that's why I want to know which way it's actually moving, that you said or you concluded that the limit does not exist. So yeah,
Okay.
for the one-sided limit, you definitely should write infinity with the corresponding sign. You will see some other examples as well. As I said, once we arrive to that example, I'll mention this again. Okay.
Would it be accurate to say that could we
Yeah,
say it
it's more
doesn't exist?
accurate. Yeah.
Could we say it doesn't exist and also that it's moving in a certain direction instead of just saying infinity? Was that accurate?
If you are given a chance to show your work, then you'll get this chance. But what if you just need to write the short answer in the answer box? You might see some questions where you just need to write the answer. It will not be multiple choice question. It will not require you to show your work. You'll just need to write the answer, precise answer, nothing else. So yeah, you can definitely write that elaborately, no doubts on that. But yeah, I think you can choose where should you write does not exist and where should you write infinity. No worries, it's still early days. You'll see examples and you will get more experience on how to choose this. And I'll definitely mention this, obviously. Okay. And as I said, if you write does not exist in place of, let's say, a negative infinity like this one, if you write does not exist, I'll not give you a 0. You will definitely get partial credits. No.
What about does not exist negative or does not exist positive?
Sorry?
Could we write a negative sign next to does not exist?
No, you can't do that.
Sorry. All right.
Yeah. And yeah, I think it's a good question. Yeah. But yeah, you can do that. Okay. All right. So in the first graph or the first pair of graphs, we can see the right-sided limit is positive infinity and the left-sided limit, the right-sided limit could be positive infinity and it could be negative infinity as well. So whenever you're approaching from the right, it doesn't really mean that it has to be a positive infinity. Even though, like this one, you can see, even though we are moving from the right, the limit actually is negative infinity. So this is the thing you can keep in mind, that whenever you're approaching from the right, it could be either positive infinity or negative infinity. Moving from the right doesn't really mean it has to be positive infinity. Okay. And same goes for the left-sided limit as well. If you are moving from the left, it could be positive infinity or it could be negative infinity as well. Moving from the left doesn't necessarily mean it has to be negative infinity all the time. Okay. It's just for your, I guess, to clarify things on your mind. All right. I may ask a question that if you're moving from the right and you're trying to calculate the infinite limit, what it should be. The option could be positive infinity, negative infinity, neither, it could be both. So you might see a tricky question like this. Okay. All right.
And you said it could be, you said one of the answer choices was positive and negative infinity from traveling from one side.
So yeah, the answer of this question would be, it could be both, right? So it doesn't really give you anything to any chance to write anything about it. Rather, you need to choose from the options. What I generally do is I tend to set up some tricky questions, some really, really yeah.
Is this is one whole graph, right? I was thinking they were separate. That's why I was kind of lost. Like this is one side above the x-axis and the one below the x-axis, but A is still the same.
So this is actually two different graphs, to be honest. It's not the graph of the same function. We're just trying to show that even if you're approaching towards the same point and approaching from the left, you could actually have positive or negative infinity. Obviously, for different functions, you can't, maybe you can have it for the same function as well. But what we are trying to show here, that moving from the left doesn't really mean that it has to be negative infinity. So you don't need to get confused by this, because this is just separate graphs to show the differences. Instead, you'll have graphs like this. Okay, you'll not be given broken graphs. You'll definitely see one particular graph to eyeball at. Does it answer your question?
Yes.
Okay, thank you. All right, are we done with that? Yeah, and here we are, vertical asymptotes. It's really interesting, and we'll use this word vertical asymptote probably 1,000 times while this course is being completed. Okay, so try to understand it completely. This is a basic concept, and obviously when you are visualizing a graph, you will definitely you'll be able to eyeball it. Okay, so let's first see the definition. So when x is approaching towards a value, so towards a certain value a, if the function approaches to infinity, it could be positive or negative. If it's moving towards any of the infinities, or even for the one-sided limits, if we're approaching towards a certain value, and if the function is approaching towards any of the infinities, then we say that x equals a is the vertical asymptote of that particular function. Obviously, you don't need to memorize the definition. I'll not ask you to write the definition anyway, but if you know the basic requirements for it, that should be enough. So this means whenever your function is approaching towards any of the infinities, whether it's positive or negative, we say that x equals a, obviously it's a line. That line is a vertical asymptote of that particular function. Now let's quickly go back to the graphs we have. Here you go. So as you can see, x is approaching towards a, and your function is approaching towards positive infinity. Can you see that? That means your that means this line, this dashed line, as you can see, since it's been drawn at x equals a, so we say this x equals a dashed line is the vertical asymptote for this particular function. The same goes for this one. On this occasion, the function is going towards negative infinity. That still meets our requirement. So this dashed line at x equals at a, that means this x equals a line is the vertical asymptote of this particular function, whatever it is. Let's see the previous graph. Here you go. So we have a dashed line at positive infinity, at positive 1. And we can see when we're approaching towards 1, the function is going towards infinity. So that means this line is a vertical asymptote. Same goes for this one as well. When we're approaching towards negative infinity from either side, we can see the graph is going towards negative infinity. So it meets our requirement. We can say that x equals -1, this dashed line is the vertical asymptote. So we can actually have more than one vertical asymptote for a particular function. Like for this one, this particular function, we have 2 vertical asymptotes. Okay. Any question from the definition?
So is it safe to assume that we always have an infinite limit at vertical asymptote?
Yeah, you're right. Definitely. Very good. Yeah, good assumption. Because the graph will never cross it, neither touch it. So yeah, definitely we'll have an infinite limit there. Yeah. Any other questions from this?
I have a question about the test.
Mhm.
Is there any restrictions that you have for taking the test? Like we can't have text or music perhaps playing through headphones, or no headphones at all, I mean.
Okay, so first of all, it will be conducted online. So it will be difficult. Yeah, it's sad but true that it will be difficult to monitor all of you at the same time. So if you are comfortable enough to have the AirPods on, I don't mind, but I'd rather suggest to avoid this. Yeah. Any other questions about the definition or anything else?
I guess to go along what he was asking. So the guidelines would be a closed book, closed note, no electronics or anything like that other than the test.
Absolutely, yeah. Once I
Okay.
set up the question, I'll make an announcement with I'll try to have clear directions, clear policies about it. Okay, I'll try to do that.
Okay. And do you also know how many questions it's going to be?
No, since I haven't really set up. So the problem is, I'm just wondering whether I should do this during our discussion time, or whether I should go for any schedule after the discussion. I'm just trying to imagine it. So, is there anyone who has a different class other than this this summer? I mean, this first half of the summer.
Yeah, I'm in fluids, but we don't have a meeting time. We just have like homeworks and stuff to do.
Oh, so it's asynchronous, right?
Yeah.
Okay. So, yeah, that's the problem. If I choose any other time, then it might not be best suit for all of you. So let me see. I think I should ask the course coordinator, because I can decide it by my own, but I think I should take his experience and see what he suggests. I'll let you know. Obviously, within this, not really within. I'll definitely let you know within Saturday, definitely. So that if you have any question or you want to have any meeting and a discussion with me on Sunday, we can do that. Okay, I'll be available during the weekend. Just let me know when should we meet. We can find a schedule which works both for us, and then we can meet. Or even we can chat via email. I generally reply within an hour, maybe faster than that.
If at all possible, can you just make the exam during the discussion time? I don't know about anyone else, but like I work for most of the day outside of this class. So it makes it easier to kind of schedule those things.
Yeah, exactly. That's why I was planning to do that, because if it's not a best suit for any of you, even one of you, then it's a problem. So I need to see what I can do. Maybe I can reschedule it for only you, or if someone else.
I'm in
also
the
has-
same boat as her, where I
Mhm.
work like from 1 to like 11 p.m. So
Oh my God. When do you study, if you don't mind to share?
like right after class for 3 hours, and then I go to work.
All right. Best of luck. I know you are having a
Thank you.
tough schedule. I'll try to keep it simple.
You
Is
can have
there-
two.
Is there any way you could do like a poll and see when it works? Like during the discussion time would be better for me because I also work 2 jobs. So
Yeah, let me do it now if you don't mind. I can do that now.
Maybe if it's convenient, you could do like 2 different tests and one with a specific time and maybe some more restrictions or maybe less restrictions, and then one without a time limit or a time due date.
Okay, having said that, I think I can do, yeah, what I can do is make it available for the whole day. And whenever you start the exam, you need to finish it on one sitting. What do you think about it?
Yeah, most of my classes have been like that.
Mhm.
I was saying in the chat, and I think it's worked for everyone in all of my classes because they could take it anytime during the day,
Right.
but we still have a time limit.
Right. So I think I can do that. So it will be available from, let's say, 7 a.m. in the morning till 11:59 p.m. on Monday. And whenever you have time, you can sit for it. And obviously, when you sit for it, when you appear for it, you need to finish it on one sitting. You can't really leave it and come back. We can do that.
So
Yeah.
if we did that, would we still have class on Monday, or would we just take the test in place of class?
So I think we still have class on Monday because I have a tentative schedule. It's not really, I don't need to follow it hard and fast, but I'm planning to follow that. And as of now, I've been successfully doing that. Let me see what we have on Monday. I think we have a really short, let's see. If you have the syllabi, you can pull it up and see. Let me do that on your behalf. On Monday, okay, yeah. Sorry, I think I got it wrong. Yeah, we can avoid the class, yeah, because I have planned it for the entire week from June 1 to June 4. I'm planning to go over 3.1 to 3.4. So yeah, I think we can have a day off and have only the exam, not the class.
Okay, thank you.
This way,
Also,
yeah.
well,
sorry.
If are you done? I was gonna go on to a different subject.
Okay, so yeah, so for Monday, so that technically means you have the whole day for the exam, okay? And once I set up the question, I'll probably do that tonight if I feel all right. I've been doing all right since I've taken the second dose, but let's see how, because the second day usually is the worst day. So let's see how do I cope up tonight. If I'm all right, I'll probably try to set up the question tonight. And as soon as I finish it, I'll definitely let you know in detail. Yeah, it will cover from 2.1 to 2.6. Yeah.
All right. Are you ready for my
Yeah.
question? All right. So I was wondering if there's any chance that if we could still do it in one sitting, the test, but maybe have no restriction on time, because I feel like the time is a bit of a distraction, like a time limit.
Okay, so yeah, I know you have a valid point, but if you don't have any time restriction, then
Maybe just a recommended time, like how long you should be spending on it.
so generally what I do, if I can do it, let's say in 30 minutes, I generally give the students double the time. So when I set up the question, if I can finish it in half an hour, I'll give you at least 1 hour, maybe 2 hours. Generally, I give a lot of time, but I tend to give the time restriction because if you have ample time, if you have, seems like infinite time, then the exam, the intensity of the exam, I guess, gets somehow reduced. That's what I feel. But if most of you think that I should lift the time restriction, I think I'm more than happy to do that.
I think maybe if we had no restriction, it would help with our success. And I think that's the most important part of the taking the test. And
Yeah, definitely. The test is here for, evaluating how well do you understand, how well you understand the concept, and how are you uh, using your concepts to, how are you implementing those to solve problems. So yeah, I agree to some extent, to be honest. But let's see. Yeah, I'll let you know. I'll definitely let you know.
I could definitely understand from your point of view. It could also offer some, I guess, unnecessary stress. If you think you have infinite time, you'll spend infinitely amount of time on it as
Right.
well.
Yeah.
All right. Thanks.
Mhm. All right. So let's take a break for 5 minutes. So we'll meet at 11:16. Okay. All right. So any question from the vertical asymptote? Or anything from the graph? I mean, why is it the asymptote, or why is it called the vertical asymptote and all that? Any question about it? All good? Okay, so let's see.
Oh,
Yeah.
one thing. Are we ever going to run into horizontal asymptotes? Or
Yeah,
those,
we'll
do
see
they
that as
exist?
well. Yeah, definitely.
Okay.
Let's see this graph. Let's say we have a function x minus 2 over x minus 1, the quantity squared, times x minus 3. Okay, so this is the graph. Again, you will not be required, you will not be asked to draw a graph. I'll not do that. If I somehow do that, just let me know that, hey, you said you don't do that, and I'll give you full credit on that. Okay, I'm pretty sure I'm not going to do that because it's not the part of this course. It's actually from the algebra course. So either the graph will be given, or if the function is given, you will not require the graph anyway. So I'll try to remember it. Okay. All right. So now the first question is, can you eyeball the vertical asymptotes? If yes, how many can you see, and where are those? Anyone?
You got two, one at 1 and another at 3.
Exactly. So whenever you see these dashed lines, and obviously we'll also see the graph will never touch, neither cross it. Even for this, you can see the graph is going really close to the dashed line, but it's not really touching it. So if you see anything like this, you can clearly say that it has to be the vertical asymptote. And obviously, if you can see it from the Cartesian coordinates, you can see that it's at x equals 1 and at x equals 3. Do you agree?
Yeah.
Okay, now why, or rather, how does that satisfy the definition or the requirements of the vertical asymptote? Let's see. So we know if you're approaching a point and if the function is going towards either side of the infinity, then we say that at x equals that value, let's say a, at x equals a, we have an asymptote. So let's see and cross-check whether that satisfies our requirements or not. So at x equals 1, we can see when we're approaching towards 1 from the left, the graph is going really close to that, but it's not really touching or crossing it. Rather, it's going upwards, and it seems like that it actually is keep going. It's actually keeps increasing. That means it's going towards positive infinity. And we know even if it's from one side, then we can conclude that it's a vertical asymptote. We don't even need to see the other side. But yeah, it's true for the other side as well. If you move from the right towards 1, you can see the graph is slowly and slowly going close to it, but it's not really touching, neither it's crossing it, and it's going towards the mega infinity. So we say that indeed we have a vertical asymptote at x equals 1. Does this make sense?
Yeah.
Anyone who is still confused, don't get hesitated, okay? Don't get hesitant. If you have any hesitations, just let me know. If you feel like doing it after we finish, maybe in email, or if you want to meet in Zoom, just let me know. I can definitely do that for you. Okay, let's see what happens at x equals 3. So when you are approaching from the left towards 3, you can see the graph is going downwards, and it keeps going, and it's not really touching, neither it's crossing that line, dashed line. That means, well, we can actually do it. I mean, we can actually draw the dashed line after we finish the graph. So this means when you see that when you are approaching from the left and the graph is actually going really close to this imaginary line, but it's not really crossing it. And same goes for this one. It's not really crossing this imaginary line. Then we can actually draw this. It's not really here right from the word go. First, we actually draw the graph, and then we see whether there's an imaginary line which the graph is not really crossing, which the graph is not touching, neither crossing. Then we draw a straight line at that point. So the dashed lines are actually drawn after we have seen that it's satisfying the requirements of the asymptote. Okay, it's not really there straight away when you draw the graph. You can do that by your hand, you know, the hand calculation won't be that difficult. Okay, any question from this? Anyone, any question? All right, let's move to the next one. We'll come back to the calculation. Let's see the graph first. So if you try to draw this graph, excuse me, where the function is x squared minus 4x plus 3 over x squared minus 1. If you try to draw it in a graphing tool, or not in a graphing tool, I should say, in a graphical calculator, you will see the graph will look like this. But it is a wrong graph. Can you say why? Anyone? It does look similar, right? But it's wrong.
Isn't it because one of the lines are touching the? Oh wait, oh, never mind.
No, it's not really touching.
Because if you put a 1 into the equation, it's undefined there.
Yeah, definitely it's undefined, but what does it, or rather, how do you conclude then that it's wrong?
Isn't it because the line represents the asymptote that runs between the two, because the lines will never touch? So it's not like a value, it's just like a representation, and that's why it needs to be like a hash mark and not a solid line.
Exactly. So the answer is the last two of you, what the last two of you said. Obviously, if you plug in 1, you get undefined value. So that means you need to have a hole here. That's the first thing. The second thing is you can't have a straight line like this here, because this actually means this is a part of the graph. This is not the part of the graph. This is actually an asymptote where you need to show it like this, because if you do it like this, it seems like it's a part of the graph. That means it's actually a straight line, which is one of the 3 parts of the graph. But it isn't, is it? It's actually the asymptote. So it has to be the dashed line. So yeah, you both are right. So combinedly, we can conclude that, yeah, we need to have a hole here at 1, because you can see if we plug in 1 here, you clearly get an undefined value. That means the function is not really defined at 1. So you need to have a hole here. And obviously, it's not really a part of the graph. It's not one of the 3 parts of the graph. It looks like on this one, though. It's actually an asymptote. It has to be the dashed line. Can you see the difference? Most importantly, does it make any sense? Because you can clearly see that the graph is quite similar, but not exactly. Any question from this? Anyone? Okay, so seems like there is no questions. And okay, so look at this one, cotangent of theta. So if you try to draw this, you'll see a graph like this, where you have 2 parts, kind of mirror image of each other. If you draw a line just diagonally in this direction, it's just a mirror image of each other. So why do you think we have this example here? Can you think of anything?
Wouldn't this be our first one to have an asymptote at 0?
Very good, very good. So what if the asymptote is actually the axis itself? Because you can see the asymptote here is actually the line x equals 0. It's this line. You can see the graph is going really close to it, and same goes for this one. It's going really close to it, but it's not really crossing or touching it. So the asymptote is actually this line, this y-axis, or x equals 0 line. So if that's the case, that means if any of the axis is not any of the, I should say, if y-axis is the vertical asymptote, then you can't really have the dashed line, can you? Then you actually have this full line. Since that's the axis, you can't really have a dashed line here. So that's one of the things. Excuse me. That's not really that important, but yeah, that's one of the things you can see. You will see in some of the problems in future. So at 0, at x equals 0, obviously on y-axis, the value of x is 0. So if that's the case, you can have the full line instead of the dashed one. That should be still fine. It should still be fine, yeah. Okay. I think we have enough time to go for the next one. Go for 2.5. Any question from 2.4? No questions at all? If you see that I'm not really responding to the chat, just unmute yourself, because often it's difficult to keep an eye on both the things at the same time, okay? Okay, let's move to 2.5 then. Okay, limits at infinity. All right, so we know how does the vertical asymptote looks like. Now we want to see how does the horizontal asymptote looks like. Okay, how does the horizontal asymptote look like? We want to see that as well, because often you will see there is a horizontal line which the graph is not really crossing. Okay, And let's see the definition first, and then we'll again go back to the graphs. Okay, now if x is now we are actually turning things around. Initially, we said x is approaching to a value and the function is approaching towards infinity, either side of the infinity. But now we want to say that if x is approaching towards infinity, then whatever the function is approaching towards, we say that's the horizontal asymptote. That means if you go towards infinity, that means if you increase the value of x, you will see the graph is still not crossing a certain value. Let's say that L. If it's not really crossing that, even though you are going towards infinity, then we say that that y equals L is the horizontal asymptote. And same happens with negative infinity as well. If x is going towards negative infinity and the function is approaching towards a certain value but not really crossing it or touching it, then we say that y equals that value. It doesn't need to be different all the time though. I mean, since it's trying to differentiate in each direction, that's why it said it, let's say it's m. So y equals m is the horizontal asymptote. Now we'll come back to the definition again. Let's see the graph. Okay. Now, let's say we are going towards positive infinity. We're going towards this direction. So as we are moving towards our right, our function is slowly and slowly going towards this. But however big the x you take, you will see the graph is not really crossing a certain value. Let's say that L. It could be any value, 5, 6, 7, or anything. The graph will not cross it, will not even touch it. It will keep going like this, pretty close to that L, but it will not cross it. Well, interestingly, you'll see some examples where it might cross it. You'll see some exceptions. We'll see those when you reach those examples, okay? Not now. As of now, as you can see, it's going really, really close to it, right? It's approaching to L. So we say that this y equals L, this dashed line, is the horizontal asymptote of this function, when obviously x tends to infinity. And for the same function, when x tends to negative infinity, as you can see, if we move to our left towards negative infinity, the function is slowly and slowly going this direction. But it will keep going this direction. It will not surpass this m, this value. So we say this y equals m, this dashed line, is the horizontal asymptote when x tends to negative infinity. Let's go to the definition again. Any question from this?
Just to reiterate, so L is for the positive horizontal asymptote and M is for the negative horizontal asymptote.
So you will have actually certain values, like this.
Oh, okay.
Yeah, you don't need to consider any L or M. It's just a definition.
Oh, okay. Okay.
I know often it looks awkward, and I know because so many letters and all that, but all of these are actually symbolic. No real values, assigned to that. Yeah, good question though. Okay, let's see this example now. Okay, so we have this graph 2 plus 10 over x squared. And if we try to draw this graph, let's say there is no dashed line here. If you just try to draw this in your graphing tool, if you can do that, not now, maybe soon after we finish, you'll see the graph will look like this. And if you draw a straight line like this at y equals 2, you will see the graph is not really crossing it. it's going really close to that, not really crossing it. So we can say when x tends to positive infinity, I mean on my right, the function is approaching towards 2. Can you see that? Slowly and slowly going towards 2, right? This graph is going towards 2. This is the, on this line, every y value is 2 because this is the y equals 2 line. So that means as we are going towards positive infinity, the function is going really close to this y equals 2 line. So that means we say that at y equals 2, we have a horizontal asymptote. Okay, same goes for this one. As we are moving towards negative infinity, we can see the graph is slowly and slowly going towards this y equals 2 line. So we say even if it was not there, the right half was not there, we still could have said that at y equals 2, we have a horizontal asymptote. Okay. Any question from this? Here we go. So as I said, if you remember a couple of minutes back, I did say that you might see some examples where the graph is actually crossing the line, but it will still say that it's a horizontal asymptote, right? I actually did say that a couple of minutes back. That's not the case for vertical asymptote though. In vertical asymptote, in no way the graph will cross that line. But for horizontal asymptote, you will see some examples like this, where the graph will eventually cross the line, but it will still say that this is the horizontal asymptote. And why is that? Since you move towards positive infinity, you will see this graph is moving really, really close to this line 5. It's not really going too far away. And if you go really, really big, it will seem like it's actually going going over that line, or it will match with each other almost. You know, as you can see, the oscillation, it's getting smaller and smaller. Can you see that? So as you go bigger and bigger, you will see this this oscillation will actually kind of match with that line. So that means since or rather, as you are moving towards positive infinity, this functional value is moving more and more towards 5. It's not really going too far away. So it will still say that it's the horizontal asymptote because it's approaching that, since as you're moving to positive infinity, the functional value is approaching to that particular line. Okay, and it will make more sense when we'll actually solve this particular graph of this particular function algebraically. You'll soon see we'll solve this type of functions algebraically, not with the graph. And then you will see for limit x tends to infinity, for x tends to infinity, the limit of this function will be 5. You'll soon see that when we'll solve it algebraically. Okay, I know this is kind of bizarre, but this is an exceptional, and you will see some exceptional examples like this, but not too many. Okay, now why do you have a graph like this where you can't really see any asymptote? This is a graph of x cubed. I guess most of you have already seen this in the algebra class or pre-calc, if not in the algebra. Let's see the definition first, okay? Then we'll go back to the graph. Am I going too fast again? Do you want me to slow down just a little bit?
It's
I
a good
think it's
pace.
a good pace.
Okay.
I just have one question. Are we going to relate these asymptotes to the equation format? Like we have yx equals a plus bx plus c plus d. I remember seeing something like that in
Yeah, definitely,
Recount.
definitely. Yeah, very good. Yeah, we'll actually do that. As I said, when we'll solve it algebraically, we'll see how to relate this to the equation format. Yeah, good point. But now we are actually working with the graphs only. That's why we're trying to visualize things, and then we'll solve some more complicated problems algebraically, because graphing all the functions is not easy. So we are observing some easier functions. Then we'll solve some more complicated ones algebraically. Yeah. Okay, now infinite limits at infinity. Okay, now what happens? What happens, or how could you define, or what should you say when you see that whenever x is moving towards infinity, the function is also moving towards infinity? So that is actually the infinite limit at infinity. We have seen both ways. We have seen x is approaching towards a value and the function is approaching towards infinity. Or we have seen x is approaching towards infinity and the function is approaching towards a certain value. But what if both of these are approaching towards infinity? That means your x is approaching to, whenever your x is approaching towards infinity, your function is also approaching towards infinity. So that's what we say infinite limits at infinity. And that's actually true for any side of the infinity. That means it could be negative infinity, it could be positive infinity. As you can see, we can have 4 different categories, for x tends to positive infinity towards fx tends to positive infinity or negative infinity. And same goes for x tends to negative infinity as well. As you can see, these 2 categories. So for all of this, we'll say that it is an infinite limit at infinity. And this is the graph. This is a graph of an infinite limit at infinity. As you can see, if we move towards infinity, the function will also move towards infinity. If we move towards negative infinity, the function is also moving towards negative infinity. Can you see that? That's why we say it's infinity, or rather infinite limit at infinity. Can you name another function like this out of your head? Pretty smallish one. You don't need to think too much to find it.
Like a parabola, maybe?
X squared.
X squared. Yeah, I think x squared fits that as well, because x squared will look like a cup, like this, like a U shape. So as you're moving towards negative infinity, it will move towards positive infinity. As you'll move towards positive infinity, it will still move towards positive infinity. Yeah, that's a good example. So any function like this, where there is no real, you will have something assigned to it as well. But if nothing is assigned to it, nothing is attached to it, all of the functions in the form of x squared, x cubed, x to the 4th, you will see all of these will have infinite limits at infinity. Parabola, yeah, parabola is a good example as well. Any parabola, any parabolic shape, yeah, definitely. It will be, because the parabola will look like this or this, I mean, on either side. So yeah, definitely. All right. How much time do you have? We have, okay, so we have almost 15 minutes. Yeah, I think we can keep doing this. Okay, oh, I see. We actually have those functions here. I didn't see that. So if you have functions like this, as I said, x squared, x cubed, x to the 4, or if you keep going like this, you will have infinite limits at infinity, as you can see. So this blackish one is for y equals x squared, red one is for x to the 4th, bluish one is for x to the 6th. So as you can see, for these even functions, whichever way you are approaching towards for x, you will see the function will eventually move to positive infinity, right? It's not going below this x-axis, is it? If we are moving to our right, it's still going up. If we're moving out to our left, it's still going up. So that means for even functions, the infinite limit at infinity will always be positive. It will move towards positive infinity. And can you tell me why? Anyone?
Is it because no matter what number you put in for x, negative or positive, if you have an even exponent, it will become a positive number?
Exactly, very good. So whenever your exponent is even, or in other words, on these occasions, your function is even, whatever you take for x, even if it's negative, you can see because of the even exponents, it will be the corresponding functional value will always be positive. It can't be negative anyway. So that's why if we go towards positive or negative infinity, either way, either case, our function will take us to positive infinity. It will never have anything negative. But what happens for the odd functions? So for the odd functions, if you take anything positive, you'll get a positive value, right? But if you take anything negative, since the exponent is negative, you will get a negative value. Do you agree? If that's the case, you can see if you are moving towards positive infinity, the function will go towards positive infinity. If we go towards negative infinity, the function will go towards negative infinity. Does it make sense?
Yeah.
Any question from this? No questions at all? Okay, let's move on then. Okay, here is the theorem. So first of all, I would like you to ask me, or rather ask yourself, how do you recognize a polynomial? When can you say, if you just eyeball an expression or a function, can you conclude that it looks like, or it has to be a polynomial? How do you recognize that? How does it look like? That's the first question you want to ask yourself. If I just give you a function, can you just eyeball and say that, yeah, it does look like a polynomial to me? Can you conclude that? Anyone? You don't need to look at the definition. I know it doesn't really look good. It looks clumsy because there are so many subscripts and superscripts here. So it doesn't really look convincing, but can you eyeball and differentiate? If I give you 2 or 3 functions, can you tell me that, hey, this is a polynomial? Is there anyone who thinks that it's a kind of tricky job?
Is it just based on their powers? Like x to the so-called power makes it a polynomial?
So what if I say I have a function x squared plus 1 over x cubed. Is it a polynomial?
Yes.
Okay, so first of all, it's a fraction, no doubts on that. So now, is it a polynomial? Well, since it's a smallish one, I mean, I have only one term in the denominator, I can actually rewrite that as a polynomial. Yeah, you're right. It's indeed a polynomial. But what if I have more than one terms in the denominator? Let's say I have x squared plus 1 over x cubed minus 3. Now is it a polynomial?
Can it only be a polynomial if it has multiple different variables, like x and y?
Not really. You don't
Okay.
need to have more than one variable. You can only have one variable. Let's say that's x or even y. It could be anything, but you can have only one variable. So here is the thing. So for polynomial, you need to have more than one term. More than one term. Now, how do you define a term? If two expression is separated by a plus or a minus, then we say those are the terms. If they are working as a product or a quotient, that's not a term. So that means x squared plus 5x. We can separate these two expressions, x squared and 5x, with that plus term, right? Those two are connected by that plus. So we say that we have two terms here. But if we had anything like that, x squared times 5x, then we say that we have actually only one term, not two. So terms have to be separated with either plus or minus sign. So this is where this plus or minus sign comes from. It can't be product or quotient. It has to be either plus, or it could be also minus. They have used plus generally because the value of these coefficients, these ANs, could be negative. So either way, it actually gives you an idea that either plus or minus has to be there. And you have to have more than one term. That means you at least need two terms here. Then you can say it's a polynomial. Okay. All right, so let's see one example of polynomial, and then we'll come back to it. Okay, so let's say this one. So let's just consider the numerator. Can you see the numerator? 3x plus 2. I'm trying to hide the denominator so that it doesn't confuse you. Can you see the numerator?
Yeah.
Okay, let me just do it like this. Okay, so this 3x plus 2, oops, sorry, has two terms, as you can see, 3x and 2. And x has an exponent of 1 here, and it has a coefficient of 3. That means if we go back to the definition, n is 1 for that problem, and your a1 is 3. Where is that? Here you go. A1 is 3. And the last term, where you don't have any x, that means the constant term is 2. So if we just consider the numerator itself, it's a polynomial. Or, oh, okay, we have it here. Sorry about that. This one, negative 2x cubed plus 3x squared minus 2. That's a polynomial. Why? First of all, we have three terms. The first term is negative 2x cubed. Second one is 3x squared. And the third one is negative 12. We have joined, or rather we have added these together with either the help of plus or minus sign. So we have three terms here. This gives us the first condition. Then we have the coefficients and the exponents of x. So here the highest power is 3, the coefficient is negative 2. Then we have the exponent 2, the coefficient is 3, then you don't really have anything with x to the power 1. Excuse me. Can you imagine the coefficient of that? We don't have anything with x. What could be the coefficient then? Anyone?
Coefficient, isn't that the leading number of the highest power?
No. For each term, we have a separate coefficient. This is the coefficient of x squared. This is the coefficient of x cubed. So what's the coefficient of x here? Since we can't really see.
0.
0, very good. We can actually rewrite it as 0 times x minus 12, right? So this actually satisfies this. That means when you are going to the lower exponents, and eventually you'll have a constant term. You don't need to have it all the time. You can have a 0. I mean, we can say like this one. We can say x cubed plus 0, right? That's still a polynomial. I mean, it's not a polynomial. It's only one term. We can say it's a monomial anyway. Yeah. So this a0 could be 0 as well. Okay, any question from the polynomials? No questions at all? Okay, let's see the theorem then. I think we can just iterate the theorem. We'll not be able to explain it today. We'll leave it for tomorrow, okay? Just see what does it say. So when x is approaching to either of those infinities, if you have a function like this, x to the n, where n is even, you can see that whatever you take in place of x, since n is even, it will take you to positive infinity. It's just the example of this one. This is x to the n, this is x to the n, right? Where n is 2, n is 4, n is 6. If n is even, if you move towards infinity, you will eventually reach infinity. And it will be positive infinity, that's for sure. And with this graph, we can see for the odd exponent, if we move towards positive infinity, if x moves towards positive infinity, the function will move towards positive infinity, and vice versa. If x moves towards negative infinity, the function will move towards negative infinity. That's what the second theorem, second part of the theorem says. When x tends to infinity, x to the n will eventually go to infinity, and when x tends to negative infinity, x to the n will eventually go to negative infinity when n is, of course, odd. This is actually rewriting the algebraic format what we have discussed for these two graphs. Okay. All right. What's the next one? What if we have a negative exponent? This 1 over x to the n signifies, or we can rewrite it as x to the negative n. Do you agree? We can rewrite 1 over x to the n as x to the negative n, right? Like this. And if that's the case, whichever direction you're approaching to, your function will eventually approach to 0. And why is that? So let's consider this one. This format will give us a better view. So if x is infinity, what's infinity to the power n? We know it's infinity, right? We know when x tends to infinity, excuse me, x to the n will eventually take us to either positive or negative infinity, right? That's for sure. So if we have 1 over infinity, we can rewrite it as 0. Anything over infinity, we can actually rewrite it as 0. Because you are dividing something by a really, really, really big number. Infinity at the bottom, at the denominator, means you are dividing it by infinity. That means you are dividing something by a huge number. So it's so big that in return, you are not getting anything when you're dividing, right? If you divide a single piece of apple into let's say 10,000 pieces, you'll eventually see there is no real piece left there. It will be all smashed. You can imagine that, right? Okay, let's stop here. We'll start from 3 again. I'll show how does it actually work. Hopefully it will make more sense to you. And we'll obviously do the other part of this 2.5 as well. So your pre-class assignment for tomorrow will be go over 2.5 and 2.6. We'll eventually complete 2.5 and start 2.6 tomorrow. So I want you guys to go over that as well. Okay.